The horizontal asymptote, we're only looking at end behaviors. Okay, to the right end and to the left end is the graph approaching some y value. For example, let me make up something. A graph. I'll make up a graph. I'll make up f of x equals 2x minus 1 over x plus 5. And I'll do a zoom out maybe. Okay, so take a look. It doesn't have asymptote graphed, but I will graph it to show you the horizontal asymptote. In this case is y equals, so I'll tell you how to find these horizontal asymptotes. But take a look at the graph. As x gets really big, in other words, as we go to the right side of the graph, do you see that this graph is approaching this orange dotted line? It will never cross it to the right end. It will just get really, really close to it. All right, I'll do it slow. Look at the y values. 1.8, 1.88, 1.846, 1.89, 1.9. You know, as x gets really big, like when x is 140, y is 1.924. So y value is approaching 2. See, it's almost the same, but when x is 323, y is 1.966. So if graph does that, okay, if graph does approach a certain y value to the right end, or it could be to the left end, you see the graph, this black graph is coming down, but it's not going down all the way. It's kind of slowing down and it's approaching the y value of 2, right? The y is getting closer and closer to 2 from above. But if the graph does that, we call this horizontal asymptote. So, the line y equals b, where did that go? The line y equals b is a horizontal asymptote of f of x if either or both of the following statements are true. And I'll write these statements. Let's review this limit notation. When x gets really, really big, okay, which means the right end behavior, if you follow the graph to the right, and you notice that the function value or y value is approaching certain number b, then that is a horizontal asymptote. So what I just wrote down, that's about right end behavior, because x is approaching positive infinity, means in a number line, you have 0, 1, 2, right? Oh my goodness, look at me, just put 2 first. 1, 2, dot, dot, dot. But if you, you know, when x gets really big, we are going to the right side. So if the right end behavior is approaching some value b, or it doesn't have to be both, it can be either or, the left end behavior. So when x is approaching negative infinity, your y value or your function value is approaching this value b, then we say this function has a horizontal asymptote of b, y equals b. So that's what the graph looks like, but the graph will look like, and numerically too, if you plug in numbers that are infinitely big or infinitely small, you'll find that y value. How do you determine that? I mean, in 161, in pre-calculus, you guys learned it by looking at degree of the numerator and the degree of the denominator. That is still the easier method, I believe. Okay, so if the degree of the numerator, take a look at this one for me, is x to the first power, and the degree of the denominator is x to the first power. Okay, when degree of numerator equals degree of denominator, then horizontal asymptote is at the ratio of leading coefficients. So I'm just kind of reviewing what you probably already know. But when these exponents, when the biggest exponent on top of the fraction and the bottom of the fraction is exactly the same, we have a horizontal asymptote of ratio of their leading coefficients. So 6/14. We should simplify that. That is 3/7, right? So that's how you find the horizontal asymptote if the degree of the numerator and the degree of the denominator are the same. But what if they are different? Look at this for me. G of x, degree of the numerator is 1, degree of the denominator is 2. I'm going to highlight those two. They are not the same. So if this happens, if degree of denominator is greater than degree of numerator, imagine this. The bottom of the fraction is getting bigger quicker, okay? So imagine dividing something by a big number. Like you divide $5 to 5 million people. How much money each of them will get? Like 0, right? So when the bottom of the fraction is getting bigger quicker because they have a bigger exponent, a bigger degree, we have a horizontal asymptote at y equals 0. Anytime the bottom of the fraction, the denominator, has bigger degree, horizontal asymptote is always at y equals 0. Okay, so we looked at two different cases. Now what about this one? What are their degrees? I'm looking that the biggest exponent in the numerator is 7. Biggest exponent in the denominator is 8. Well, this is the same case as before. Degree of denominator is greater than degree of numerator. That means when we plug in infinity, or when we plug in a really big number, the bottom of the fraction will be much bigger than the top of the fraction. Okay? So if that happens, you're dividing a value by something really big. And when you do that, the quotient will approach 0. So I hope this is a review, because if this is the first time you're seeing this, I am going over this way too quick. So if you want to talk to me about more of these cases, let me know. I think I can find some pre-calc videos and post those for you on Canvas. All right, but let me finish this up. Oh, now we can't use that for this equation, right? Because this doesn't have the denominator or numerator. This is not a rational function. So how would you do this? Okay, so we have to do this using calculus. Think of two cases. The right end behavior and the left end behavior. So, I guess the easier way to do this is just kind of quickly sketching it to see what the graph is doing. I'm going to see what it is doing. The graph is 4 times e to the 8x power. Why is that so beautiful? What is that? What did I just see? Okay, maybe nothing. But do you see this graph? Take a look at the right-hand side of this graph. What is the graph doing to the right side? It's increasing without bound. It's not approaching a value. To the right side is going up like crazy. So graphically, what we just saw is that limit as x approaches positive infinity, a p of x does not exist, or I should say is equal to positive infinity. It's not a real number, so I can say that it doesn't exist. But we can't graph a horizontal line up at infinity, so if that happens, we don't have a horizontal asymptote to the right side. But look at the left tail. I want you to look at the left tail. What's happening here? When I go to the left side of the graph, is the y going down without bound? look at the y values. As I keep on going to the left, do you see that the y is approaching 0, right? So this graph has a horizontal asymptote of y equals 0 to the left side. And horizontal asymptote doesn't have to be the same to the right side and the left side. I mean, this graph right here doesn't have a horizontal asymptote to the right side. But to the left, as x gets, and I will write that down, what we have is as x approaches negative infinity, so to the left side of the graph, we can obviously see that p of x is approaching 0. Therefore, this graph has a horizontal asymptote of y equals 0. But that's using graphing calculator. So how would you do this without a graphing calculator? All right, so imagine this. We'll just evaluate this, okay? Limit as x approaches negative infinity of 4e to the 8x power. Now take a look. Well, it's awkward to plug in negative infinity, but imagine that for me. If you plug in negative infinity, what will happen is this term will go to the bottom of the fraction, don't you think so? Because when you plug in a negative number here, like negative 1,000 or negative 5 million, the exponent becomes negative. When it becomes negative, we're going to send it to the bottom of the fraction. So what we will have is this. Okay, and I'm going to hate what I'm writing, but this is what it is. 8 times negative infinity. I know it's great. I'm sorry. This looks bad. I shouldn't. But hey, you get the idea, right? Well, whoopsie daisies. It's not negative anymore, right? We sent it to the bottom. So now it is positive. So look at this for me. We're dividing 4. We're dividing 4 by a really big number. Okay, so if I use a scientific calculator to test some values, what will happen if I do 4 divided by e to the 100th power? I guess I don't even have to go that small. What if I do e raised to the 5th power? It's approaching 0. 4 divided by e to the 5th power, 6th power, 7th power. You see, as exponent gets bigger and bigger in the denominator, the quotient is approaching 0. Because if you divide 4 by a really big number, you get 0. When the bottom of the quotient is very big. Hey guys, you remember this little theorem, right? Limit as x approaches either positive or negative infinity of k over x. I think we talked about this when we did limits a couple sections ago. That's automatically going to be 0 because dividing any number by a huge number or a very, very, very like big, small number, okay, like negative 1 billion, that's going to give you 0. So I think the last one was a little bit tricky, but hopefully seeing the graph and just hearing what's happening, like dividing by a big number, that helps you understand that this graph has a horizontal asymptote at y equals 0. I'll come back and do a little more of evaluating limit at infinity. So this will be review for you that you did last unit, but I'll come back and go over those again too.